This is the first lesson in Chapter 2. We have 3 lessons to cover in Chapter 2, which means we'll be finished the unit on Wednesday, Thursday before the long weekend, and Tuesday after the long weekend. We will be reviewing, and your unit exam is on Wednesday of next week. There's a big part of me that wants to tell you that there's nothing really new in this lesson. All we're going to be doing is learning how to apply transformations, all of the transformations that we've learned, except for inverses. We're back to the A, B, H, and K thing. We're going to be learning how to apply all of those transformations to a new function. The only thing that's really new is a new function, but we're still applying all of those transformations to it. The new function is f of x equals root x. So you need to know what f of x equals root x looks like. You need to be able to apply A, B, H, and K effects to f of x equals root x, and tell me about the resulting function, domain, range, all of that information. So just to put this into context, if you know the properties of the following functions, you should know the properties of any of their transformations. In grade 11 math, you learn what f of x equals x squared looks like. It's a parabola with its vertex at the origin, and based on that, I would expect everybody in the room to be able to tell me about any form of that x squared after you apply A, B, H, or K to it. All right? And that's almost a grade 11 thing, except in grade 11 you steered away from B. You never really had a B for x squared. F of x equals x cubed is another basic function. You may not know what it looks like, but sooner or later you're going to be taught what it looks like. And if you do know what it looks like, then you should be able to graph any transformation of that. All right? And please don't get ahead of me in this lesson. Please focus on what we're talking about here. Just in general, f of x equals x to the n, whether it's x to the 1 or to the 2 or to the 3 or to the 4 or to the 100, you will learn later on in the next unit what these functions look like, and you should be able to transform them. Some other functions that we're going to be learning about, 2 to the x, you have no idea necessarily what it looks like. Absolute value of x, well, that's from grade 11. So even from day 1 here, I assumed you could transform f of x equals the absolute value of x by using h and k. And then by the time we got to day 3, by using a and b. Sine x, cos x, log base 2 of x, these are all functions, 1 over x, that we're going to be learning throughout the year in different places, and you have to be able to apply a, b, h, and k to them. Well, all I'm telling you is today we're focusing on this function, okay? That's it. Some of the problems get quite challenging algebraically, but there's nothing new conceptually. So what is a radical function? It's not a crazy function. A radical function is any function where the independent variable is part of the radicand. A radicand is the thing that's underneath the square root. Now, radicands are also things under cube roots and fourth roots, but here we're talking about radical functions as being square root functions, specifically square root functions. So these are all examples of radical functions, because the independent variable, which is always x, assuming that x is the variable on the bottom axis. X could be time, but the independent variable x is underneath the radical sign. So those are examples of radical functions. So as a warm-up, we're going to graph using a table of values what y equals root x looks like. And when you look at this radical function, I'm calling it the most basic radical function, that square root symbol has a very specific meaning. It's called the principal square root, and it means the positive square root. So don't be duped into believing there's a plus or a minus there. There is no plus or minus there. There's only a plus or a minus in front of a radical sign if you take the square root of something to introduce the square root. But otherwise, it just means the positive square root. So we're going to complete this table of values. I hope you understand why I'm choosing the x coordinates in my table of values that I am. They all happen to be perfect squares, so when I take the square root of them to get y, I get y equals 0. The square root of x when x is 1 is 1. The square root of x when x is 4 is 2. All we are doing is taking the square root of these key points. Could I have in here x equals 3? Yeah, then the y coordinate would be root 3, but that's kind of a clunky thing to locate on the grid, because then you have to put it into your calculator, and your calculator gives you a decimal approximation, which is like 1.73 or something, and it's hard to locate. These are going to be right on what I call the crosshairs of the grid. So root 9 is 3, root 16 is 4, root 25 is 5. What we're doing here is not really math 30. I'm just introducing you to what this function looks like. So it does have what we would call a vertex. It's not a vertex like a parabola's vertex, but it's kind of a starting point, 0, 0. And then when you go up 1, you go over 1. When you go up 2, you go over 4. And I want to stop for a second and just get you to watch me. Because y equals x squared, which is not this. I'm talking about y equals x squared. From the origin, you should be familiar with you go over 1 and up 1, over 2 and up 4, over 3 and up 9. Of course, you're going in both directions. This is actually half of the inverse of y equals x squared. It's laying on its side, but it's only the top half. So instead of going over 1 and up 1, over 2 and up 2, you're going up 1 and over 1, up 2 and over 4. And I believe I misspoke a minute ago. Instead of going over 1 and up 1, over 2 and up 4, you're going in the opposite order. You're going up 1 and over 1, up 2 and over 4. So the pattern should be familiar to you. And if you take a minute, you can plot all of those points. And usually on written response, if you were ever asked to sketch things, they may be curvy, but a lot of the time they involve line segments connected to curves. So you're not really at risk here if you're not a very artistic person. What I'm getting at is I don't expect everybody to be able to draw a perfect smooth curve through all of these points. We will do our best, of course, but I recognize that depending on your skills artistically and how much coffee you have either had or not had this morning, it may be a different picture you're looking at once you graph it. Okay? So that's what it looks like. What is the domain and range? The domain is that x is greater than or equal to 0, and the range is that y is greater than or equal to 0. Pretty basic stuff. So some radical functions, but not all radical functions, can be graphed by transforming this beast. Okay? Not all of them can, but many of them can. If you apply our template transformation of y equals af of b bracket x minus h m bracket plus k to f of x equals root x, that's what you get. Now, why do you get that? Well, f is the square root in f of x equals root x. The function is square rooting. So if I have f of b bracket x minus h, then I'm going to take the square root of b times x minus h. Then, of course, I have a in front and plus k at the end. So this is the transformation that happens. We could apply that same template to any function, but today we're looking at root x. And it's not on your formula sheet, but it will give you an idea of how a, b, h, and k fit into radical functions. So we're going to go through some examples here. Sketch the graph of each radical function using transformations of the most basic radical function and everything we know about a, b, h, and k, and then state the domain and range. So on your grid here, I've given you the graph of y equals f of x, where f of x is root x. I've given you that. That's the starting function. I don't know if I've written A equals B equals H equals and K equals on your handout, but you need to write this down. You need to identify what A, B, H, and K are. You do have to move that 1 to the other side. Well, you don't have to, right? But how many of you prefer to see that K on the other side? I think that's most of us. When you move the K to the other side, you see that K is equal to -1. A is the number in front of the function, and the function is the square root, so A is equal to 3. We have in brackets x minus 5, and that's x minus h, so h is 5. And then we have a number outside of the brackets that x minus h is being multiplied by, and that number is -1. Are you all with me on those values? Okay. So what does the 3 do? The 3 stretches the entire graph vertically away from the x-axis by a factor of 3. What does the -1 do? Well, it's going to reflect the graph horizontally across the y-axis. But I want to point something out to you, and this may be helpful or not, depending on how you proceed in these questions. A and B will not affect this point, which means that the only thing that's going to affect that point is h and k. And this is very similar to a parabola, that the vertex of a parabola is always at h comma k. Well, this key point, which you can loosely call a vertex, is also going to be at h and k. Because if I stretch that graph vertically by 3, it doesn't move that point. If I reflect it horizontally across the y-axis, it doesn't move that point. That point is going to end up being at 5 comma -1 after all is said and done. That's a fact. And this will be important, this idea of using h and k to begin with, even though we're supposed to do A and B first. This will be important in various places in this course. But let's get back to these key points. We also have, so this point ends up going over to this location. What about this key point? Well, if I stretch this vertically by a factor of 3, it's going to end up here. And then I'm going to reflect it across the y-axis, which will put it here. Now, I have two options at this point. I can take that point where it's residing right now, and I can move it 5 to the right and 1 down because h is 5 and k is -1. Or what I can do is I can look at the relative position of this point compared to that vertex. And I can see that in relation to that vertex, it's 1 to the right and 3 up. So I could just do this. But again, the other possibility is to go 1, 2, 3, 4, 5, and 1 down. I want you to make a general observation here that the original function started at a particular point and went up and to the right. This graph is going up and to the left because of the horizontal reflection. I think all we need to do is one more key point. And the other key point I'm going to use happens to be underneath this, because that graph does pass through 4, 2. So we're going to take this key point, which is on here. Don't forget, this is the new point. And we are going to stretch it vertically by a factor of 3. Reflect it across the x-axis and then go 5 to the right and 1 down. And then we can sketch it. And we can write the domain and range of that resulting function. And I think we're all okay with the domain and range. I do want to point something out to you, and this doesn't need to be formally written. It's something that you're going to have to know, though. I'll write it down anyway. That those numbers are h and k. And that should make sense. The reason why y is greater than or equal to -1 is -1 is the y coordinate of that vertex, which is k. The reason why x, by the way, the reason why x is not greater than or equal to 5 is because b being negative reflected things horizontally. But the reason why x is less than or equal to 5 is that 5 is the x coordinate of the vertex, which is h. Any questions with A? All right, take a minute here and write down what A, B, H, and K are. And hopefully you're not getting caught with the forgetting to factor B thing out at this point in the course. When I rewrite this function so that it's matching my template structure, it's 2 times f of, or square root of, b, which is 2, times in brackets x plus 6, and then plus 3, which means that h is -6. And even though we're coming back from a 4-day long weekend, I hope you'll notice that even in the previous example, I didn't say on the board, I didn't write A means vertical stretch by a factor of 3. These are things we should know. And again, I'm in teaching mode, you're in learning mode. We don't need to write down every little detail. What does the -2 do to every point? Well, it's going to take every point and vertically stretch it by a factor of 2 and reflect it across the x-axis. What does the b equals 2 do? Well, this one I will write down, only because there's another little wrinkle here that I don't want you to forget. B is not the horizontal stretch factor. B is the reciprocal of the horizontal stretch factor. So B is going to take every point on the function and move it half as close to the y-axis. It's going to stretch things horizontally by a factor of a half. Then we're going to move everything 6 to the left and 3 up. However, again, this key point to begin with, we can do a few key points here. This first key point, which is at the origin, is not going to be changed by the effects of A and B. A is a vertical reflection and a vertical stretch. B is a horizontal stretch. Because the coordinates of that key point are 0, 0, they are not going to move. So the bottom line is that this key point is going to end up being here. That's a fact. A and B will not move it, but if I move it 6 to the left and 3 up, that's going to be the location of its new home. What about this key point? Well, I'm going to reflect it vertically, which is going to land it there. I need to stretch it vertically by a factor of 2, which is going to put it here. I need to stretch it horizontally by a half, which is going to put it here. And then I need to move it 6 to the left and 3 up, which I can do. I can move this point 6 to the left and 3 up, or I can look at the relation between these 2 points in terms of where they're located. And I can say that that second key point is half a unit to the right of the vertex and 2 down. If I go back to the idea of actually moving it 1, 2, 3, 4, 5, 6, and 1, 2, 3 up, you can see that it is half a unit to the right of the vertex and 2 down. think one more key point is needed. Let's take this one. Reflect it vertically by a stretch it vertically by a factor of 2, which will put it twice as far away from the x-axis. Stretch it horizontally by a factor of 1/2, which will put it half as close to the y-axis. I might have misspoken a minute ago when I said twice as far from the x-axis. I might have said y-axis. I apologize if I did. So going back to the beginning, reflect it vertically across the x-axis, stretch it by a factor of 2 relative to the x-axis, stretch it by a factor of 1/2 relative to the y-axis, and then move it 1, 2, 3, 4, 5, 6 to the left, and 1, 2, 3 up. So what this graph will look like, do your best with your steady hand, is something like this. And we can say for the domain of this new function that x is greater than or equal to -6 and y is less than or equal to 3. Again, it shouldn't be lost on you that these numbers are h and k, that this is h and that this is k. Any questions with B? So this function in example 2 is a transformation of root x. And if you like, you can put root x on here. You don't have to, but here's the first few points of root x. So we're taking that function y equals root x and transforming it into g of x. And Alice, Betty, and Chandler are all going to do it differently. They're all going to get the right answer, but their equations will be arrived at differently, and their equations will look different. What Alice assumes is that this, clearly, I hope you know clearly, these 2 points have to be sister points. Right? There's no question about that. That this vertex at the origin has to become the vertex on g of x. But what Alice is claiming is that point P is the result of moving the point 1, 1. And I know that many of you will probably say, well, how else could you approach it? Let's go through, we'll do Alice's work first, then we'll worry about Betty and Chandler. So Alice is assuming that this point P, which is at 4, 1, was the original point 1, 1. Right? She's saying, here's the origin, and that's the vertex of the original. She's saying these 2 points coincide, and she's saying that this point turns into this point. Are you with me on her reasoning? So if that's the case, Alice can determine the parameters a, b, h, and k without doing any algebra. No algebra. Clearly, the vertex is at 7, 5. Am I reading that correctly? Okay, so that means h is 7 and k is 5. I'm not sure, just because Alice isn't going to use algebra, I'm not sure her approach is the best approach, the easiest to follow. Looking at the graph, I think it's pretty clear that both a and b need to be negative. Because the original function, and I can draw in the original function if you like, I will draw it in green. The original function goes from the minimum point up vertically, but the resulting function goes from a maximum point down. It's been reflected vertically. And since the original function points to the right and the new function points to the left, there's also been a horizontal reflection. So A and B are both negative. And I do like Alice's approach. I really do. What Alice does is she looks at the vertical distance between those two key points on the original function. And the vertical distance is 1. And then Alice looks on the new function at the vertical distance between those two key points. And it's not 1. It's bigger. It happens to be 4 times greater, which means in Alice's mind, things have been stretched vertically by a factor of 4. And she's right. They have been stretched vertically by a factor of 4, which means that A must be negative 4 when we combine that idea with the idea of a vertical reflection. The thing that makes Alice's approach difficult is it's hard to put into words. Algebra is easier for an explanation because you just do the algebra, okay? What Alice also does is looks at the horizontal distance between these two key points. And the horizontal distance between them, to begin with, is 1. But when she looks at the horizontal distance between them here, the horizontal distance is 3. So to get this point, which is labeled P, at its location, it involved a vertical reflection, a vertical stretch by a factor of 4. It involved a horizontal reflection and a horizontal stretch by a factor of 3, which puts B at 1/3, negative 1/3. What does that mean? Well, it means that y is equal to A, let me write this out, AF of bracket B bracket x minus h n bracket plus k. So let's build the function. Y is equal to negative 4 f of, well, f is the square root. We went over that on day 2 of this unit. We said f means the main function or operation in the function. And in this case, it's the square root. And then we have b, which is negative 1/3, x minus h, and then after the function operation, we have plus 7, plus 5. So that is the equation of the function of that graph. And I'm not going to do this right now because I don't know how much time we'll have. If you plotted that on your calculator and you compared it to the picture, it would match, okay? It's correct. Now let's take a look at what Betty says. What does Betty say? Betty assumes there's a vertical stretch but no horizontal stretch. And some of you will wonder how that's possible because clearly there's a horizontal stretch. You're wrong if you say clearly there's a horizontal stretch. There's a horizontal stretch if you assume 1, 1 turned into P. But maybe P is there for a different reason. So Betty is assuming there's a vertical stretch but no horizontal. I'm just going to write this down here because it's in front of you, but I can't see it. So there's a vertical stretch, but no horizontal. Did I get that right? This is Betty. This is her reasoning. Okay. So we're going to write A equals B equals H equals K equals. Well, H is still 7, K is still 5. That's a fact. And by the way, I like Betty's approach better than Alice's, and I also like Chandler's approach better than Alice's because it's algebraic. We don't have to think. There's no horizontal stretch, but that doesn't mean B is 1. There still has to be a horizontal reflection. Right? It is backwards left to right. It's pointing from the vertex to the left instead of vertex to the right, which is what root x does. And now we have A, which we don't know. I love this approach. It's not going to take us long. A is a missing parameter. Let's build the equation. our equation is going to be y is equal to a root b x minus h plus k. So how are we going to find out the value of the parameter a? Who can tell me? Paige. Right. Anytime you have a missing parameter, take the coordinates of a point that you know exists on the function and load in the x and y values. You know me by now, whenever I do this, I tend to like the idea of looking at a table of values, because I'm telling you then that when you use x equals 4, you get out y equals 1. So we're going to do that. I'm going to put 1 for y, for x, and I'm going to solve this equation, which is really, it's nothing to solve. It's not a big deal. If we clean up these numbers inside of the square root, we get the number 3, I believe. Negative 1 times negative 3 is 3. So if I subtract 5 from both sides, I'll do this in steps. I get a root 3 plus 5. I need to subtract 5 from both sides, and then divide both sides by root 3 and get this. So here is Betty's equation. Y is equal to negative 4 over root 3 square root negative 1 x minus 7 plus 5. All right? Betty's answer. And I will tell you right now that if you plot that in your calculator for y1 or y2 or whatever y you want to use, it's going to match the picture given in the question. In other words, this equation, although it looks different than Alice's, is the same as Alice's. And we'll compare all three in a minute. Any questions with the work we did in B for Betty? All right, let's take a look at what Charles does. When you go back to the top of this question, it says that Charles assumes that there is no vertical stretch, but there is a horizontal stretch. Am I right in saying that? All right, so we should be able to write down some information here about A, B, H, and K. Oh, and by the way, when we figured out A here for Betty, notice we got a negative number, which we have to get a negative number because the thing has to involve a vertical reflection. But we didn't need to think about it. So what is Chandler doing? Chandler is saying there's no vertical stretch, but Chandler is smart enough to know there is a vertical reflection. You can't run from that idea. You have to be able to think or reason that out. He does not know B, but he does know H is 7 and K is 5, because that's where the vertex is. When Chandler loads the parameters into his function, he gets y equals negative 1, f of, which is the square root, b, which he does not know, x minus h, which is 7, plus 5, which is k. How are we going to find b? Well, you're going to load in an ordered pair because b is a missing parameter. And the ordered pair is still 4, 1. So what happens here? Let's see. We get 1 equals negative 1 root b 4 minus 7 plus 5. So I have 1 equals negative 1 times the square root of b times negative 3 plus 5. Well, I can subtract 5 from both sides and get negative 4 is equal to negative 1 root. I'm just going to write this as negative 3b. divide both sides by -1, I get 4 equals the square root of -3b. If I square both sides, I get 16 equals -3b. So b is -16/3. And again, I'm an algebra person. Sometimes the most difficult problems are the ones that you can't solve with algebra. You have to reason them out. And I would rather be faced with something that is very linear in my thinking, that I build an equation, I have a missing parameter, I put in numbers, I solve it. If I take a look now at what Chandler gets y equals a, which is -1, root b, which is -16/3, times x minus 7, and then plus 5.